Good morning everyone, my name is Saitija from ECC section. Today my topic in probability theorem and stochastic process is Bayes theorem with proof. Bayes theorem. The Bayes theorem is also known as Bayes rule or Bayes law. Is a result in probability theorem that relates conditional probabilities. If A and B denotes two events, P A of B denote the conditional probability of A occurring and given that B occurs. The two conditional probability A given B and B given A are generally different. Bayes theorem gives a relation between A given B and probability of B given A. The formal theorem, Bayes theorem is invalid and interpretation of probability. However, it plays a central role in debate around the foundation of statistics. Frequently, and Bayes' interpretation disagrees about the kinds of things to which probability should be assigned in applications, where the frequently assign probabilities to random events according to the frequencies of occurring or to be subsets of population as properties of the whole. The Bayesian assign probabilities to propositions that are uncertain. A consequence is that Bayes has more frequent occasion to use Bayes theorem. The articles on Bayes probability and frequency probability discuss the debate at greater length. Bayes theorem relates the conditional and marginal probability of stochastic event A and B. Probability of A given B equal to probability of B given A into probability of A by probability of B. Each term in Bayes theorem has conventional names. Probability of A is the prior probability or marginal probability of A. It is a prior in the sense that it does not take into account any information about B. P of A given B is a conditional probability of A given B. It is also known as posterior probability because it is derived from or depends upon the specified value of B, and the probability of B given A is conditional probability of B given A. P of B is prior or marginal probability of B and acts as normalizing constant. Derivation. To derive the theorem, we should start the definition of conditional probability. The probability of event A and given event B is probability of A intersection B by probability of B. Likewise, the probability of event B given event A is probability of A intersection B by probability of A. Rearranging and combining these two equations, we find probability of A given B into probability of B equal to probability of A intersection B equal to probability of B given A into probability of A. This lemma is sometimes called the product rule for probability, dividing both sides of probability of B. Providing that is non-zero, we obtain Bayes theorem. Probability of A given B equal to probability of B given A, probability of A by divided by probability of B. Bayes theorem is often embellished by notifying that probability of B equal to probability of A intersection B plus probability of A bar intersection B equal to probability of B given A into probability of A plus probability of B given A bar into probability of A. And AC is a complementary event or A bar and it's not A. So that theorem can be restated as probability of A given B equal to probability of B given A into probability of A by probability of B given A into probability of A plus probability of B given A naught into probability of A naught, where A, for more generally, where AI forms a partition of event space. Probability of AI given B equal to probability of A given AI into probability of AI by the summation of probability of B given AI into probability of AI. For any AI in the partition, see all the law of total probability. Bayes theorem for probability density. There is also a version of Bayes theorem for continuous distribution. It's somewhere harder to derive since probability density, strictly speaking, are non-probability. So Bayes theorem has to be established by limited process, as shown in figure. f of x by y, x given y equal to f of x comma y by x of y. F of x by x comma y is given as f of y given x into f of x by f of y, and there is an analog statement of law of total probability. F of x given y equal to f of y given x into f of x by integration minus infinity to infinity f of y given x into f of x into dx. As a discrete case, this term has standard names. F of x comma y is the joint distribution of x and y. F of x and y is posterior distribution of x and given y equal to y. F of y minus y equal to L of y is a function of x and childhood likelihood function of x given y comma y. F of x and f of y are marginal distribution of x and y respectively, with the f of x is being prior distribution of x. Thank you for giving this opportunity.